Welcome, folks. We're going to get this session started. So please join me in welcoming for our next presentation, Patrick Hoefler for processing large geospatial data sets with Dask and Xarray.
Thank you. My talk today will focus on array computing, and specifically we will look into what you can do to process like large or really large geospatial data sets. Like that mostly means that we are dealing with data that has more than 2 dimensions. So just a very quick intro before we get started. Like I am a software engineer at Citadel, but what I will talk today about is like about my open source involvement, not about my day job. And I'm a pandas and Dask maintainer. As I said, sorry for the title, the geospatial is a little tricky. We will look into how Dask can be used to process like terabytes, hundreds of terabytes of data, and how well or not so well that will work. I split this into 4 chapters. Like we will take a quick look at what Dask and Xarray are, for those who are not familiar. Then we will look into something that I call geospatial benchmarks. Before we take a deeper look into one of the benchmarks that we have, like it's a bias correction step. And then we will do a brief outlook and figure out what we've learned today. So Dask, at its core, is like a library for distributed and parallel computing, but it offers integrations with other tools, for example, like Xarray or like pandas, where you can scale specific data sets to a larger than 1 machine scale. Xarray, for those who aren't familiar, is like NumPy to some degree, but it allows you to add labels to your arrays. So everything in the Xarray world is mostly an array, so 1 to n dimensions basically. But you can give names to your different axes. So in NumPy it's just like 0, 1, 2, 3, whatever. While in Xarray you can tell Xarray that my 0 dimension is time. And 1 and 2 is like latitude and longitude for coordinate systems. And then you can add more like dimensions. For example, if you process satellite data, you have the satellite band as a 4th dimension. And then on top of that, you can also assign coordinates to each dimension. Instead of like accessing stuff positional, you can say my time axis runs with a daily frequency from like 1970 to 2000, so 30 years. And then selecting into this becomes a lot easier than if you have to say, okay, I want the 128th index, and that might be correct, or like maybe I have to switch one up or one down. So it just makes like accessing arrays a lot easier. If you use Xarray, like with in-memory data, it will just fall back to NumPy for all the computations. So that is like basically using NumPy, but with labels on top of it. If you use large data sets with Xarray, then NumPy isn't really an option anymore. NumPy works on a single machine. Depending on your machine, it can be dozens of gigabytes. But at some point, you'll run out of memory, and then things will get a little tricky. This is where Xarray then defaults to Dask. So if you read in a very large data set, like what I have here on the screen is, we are opening the NOAA water model. This is like information about the water depth in the United States for, I think, like 40 years or so. So this is pretty huge. And then Xarray will like figure out, okay, my input data set is chunked, and use Dask to represent that. Under the hood, Xarray will use a Dask Array. Dask Arrays is basically like the NumPy API, but for distributed compute. So in the sense you have an array that has the same properties as a NumPy array, and it has like, this one has 250 terabytes, so that wouldn't fit in a single machine, like at all. What Dask does under the hood is it like splits this array up into many, many, many small chunks. Generally a good size is like 100 to 300 megabytes, and each of these chunks is then a NumPy array. So in our example here, we have like 209 megabyte chunks. And we have like, this is a large number, approximately 1.3 million of those. So our 250 terabyte data set is broken down into like 1.3 million pieces that we then can run compute functions on. So for example, if we sum this up, Dask would sum each individual chunks like 1 million times, basically, and then concatenate all of the numbers together and compute your final result. This makes things like faster, but performance isn't really the main focus here. It's more scalability. You can process as large data sets as you want, basically, because you're not limited to a single machine's capabilities anymore. You can, for one, use a cluster to compute stuff, but Dask also basically leverages a MapReduce paradigm, so it only loads into memory what it needs at a specific time. So in theory, I could process, if I want to compute a sum here, I could process this on my laptop. That would take a while, but it would work. And if you then look at the result that we can produce, this is the water depth in the United States for 2019 and 2020. So blue means it's water is closer to the surface, while brown means that it's deeper down. So basically the Great Lakes area is where you have the most water, while out in the west where it's very dry, it's very, very brown. This was 12 terabytes of data, and Dask basically processed this on a cluster with 50 machines in a few minutes. So this is an intro about what Dask can do here. We will today focus about the Dask Array, on the Dask Array integration and not on Dask data frames or any other APIs Dask offers. But if you want to chat after, then please stop by. I'm around today if you have more questions about this. Next section is geospatial benchmarks. What is this? If you run tabular compute, for example, stuff with Spark or with any of the other tabular processing tools, you have dozens of benchmarks that you can compare tools against each other to get an idea who is performing better, who's worse, who scales better, who's more reliable, and whatever you care about. But in the geospatial world, this doesn't really exist. First, let's start why we care about benchmarking when we develop Dask. When we started working on Dask data frame 2 years ago, Dask data frame was objectively pretty shitty at scaling above hundreds of gigabytes. So what we did is we picked a benchmark where we knew that Dask wasn't performing very well on, and used this as our baseline, and then we added many, many improvements on top of it. And so, but with the benchmark, we had a good comparison against to see how well our implementation efforts actually impacted real-world workloads. Generally, in distributed computing, this is a topic that we'll go through this talk. It's not important that you do one thing very well. It's important that you don't do anything very poorly. So even if you have the best engine that's out there for 99% of the workloads, if you have one specific operation that is very, very bad, this could screw up your whole workload. So it's more like fixing dozens of paper cuts instead of optimizing something to the death. And with that approach, a number of improvements we stacked on top of each other for the data frame API basically got us a 20x improvement. But only doing one of them at a given time would have wouldn't have impacted our result that much. So this is what we were looking for in the array space as well, to get a better idea where Dask wasn't performing very well. It's not to compare ourselves against some other tool, and brag about our performance or reliability or whatever. It was more to have something at our hands that we could use to see where Dask fell apart. The benchmarks we were looking for is benchmarks of end-to-end workloads. So as I said, it's important that you don't do anything very poorly. So we wanted something that goes from loading the data, doing all the transformations, and then doing whatever you need with your output, storing it back to ZAR or printing a plot or whatever. Because if one of these components didn't perform very well, there was a good chance that the whole workload didn't perform well. Also, it should operate at large scale, so not something in the low gigabytes or medium gigabyte space, so more terabytes and above that. And it should represent real world workloads. Sometimes you end up optimizing for something that's never going to get used in the real world, and then you spend a lot of time doing basically nothing. We wanted something that's actually used out there by scientists or other corporations that work in this space. We asked the Pangeo community and the geospatial community as a whole for help. And we got lots of interesting responses. This ranged from very specific scientific workloads like climatology calculations, zonal averaging, atmospheric circulation, to more general purpose things like rechunking, regridding. These are all things that you have to do when you work with raster data or satellite data processing. One of my favorite benchmarks, because it blew everything up, was like when you process stuff from the planetary computer. That can range from being like a terabytes of data to pulling in petabytes of data if you need a really large data set. So the interesting part here is, as I said, we wanted to investigate what didn't work. Not what actually Dask did well, but more like, okay, like here's a small problem that we can fix, there's a bigger problem that we have to fix, things like that. So we ran all of these benchmarks on basically like a couple terabytes of data so that we wouldn't have to wait forever. And then we got the results back. This was me. The list of things that did not work was pretty long. And the things that actually performed well was basically non-existent. So Dask fell apart for all of these benchmarks that we had. The reason why is something we will look into now on one more specific example. The things we observed is like, as I said initially, Dask chunks your data into smaller bits of NumPy arrays. Turns out this is pretty hard. There's a reason that chunk size is 3 times up there. Then also the next thing is like Dask translates your computation into a computational graph, which means that it will execute each bit individually, and if you like end up with a huge graph means more than a couple millions, then Dask won't perform very well, and if you go further above that, it will basically fall apart. So a gigantic number of tasks is like a huge problem. And then there are more technical things that we observed that break a huge class of workloads. It's like queuing. This is when Dask, basically you have a data set and then you want to do some stuff, but Dask decides, okay, I load all of the data now, my 250 terabytes, and then I'll start doing something else, which is obviously not great because you need 250 terabytes of memory to even start processing. And quantiles, this is something we will discuss in detail later. This was actually a huge problem, even though it sounds like a niche topic. What we'll look into now is like a bias correction step that is used in a number of workloads. What means bias correction is basically we want to smooth out outliers. The person who brought this to us was like, okay, here's the 5-line code snippet that what I want to run. But obviously Dask didn't work. So this is the 300-line code snippet he actually got. Like he worked around so many bugs. And he had a lot of nested for loops that picked out Dask cells, Dask chunks to build his computations. It was pretty horrific and took me like at least a week to fully understand what he was doing there. So what he had is like, this is an array. It's pretty small, only 35 gigs. But we will do some weird shit later on that will explode the size into the double-digit terabyte size. This is a grid of data this is roughly Australia, like it's a 10-kilometer resolution, and you have 400 latitude coordinates, 500 longitudes. This roughly fits Australia. And we had, like, I think 130 years of data, from 1970 till 2100. Obviously, we're in 2025. So everything after this was a projection for the future. And they were doing some scientific analysis on that, but that's out of scope here. So the bias correction step worked with rolling windows. So if you have a time series and there's like, obviously this is a huge outlier. They were like measuring temperatures over the year. And if you like have such outliers, you want to like remove them so that you don't screw up your whole model. So what they do is they apply a rolling window and calculate the quantiles. I think they were using the 75 percentile. I'm not 100% sure anymore. So what Dask does is it basically puts a window over the dataset size and then moves this along over the time axis. The tricky bit here is that we have to do this for every x and y coordinates. So we will end up with lots of windows. And this basically moves along. And in code, this is as simple as like just telling Xarray that you want to do a rolling window. And then this is the tricky part, like if you do a sum, then there is a single pass moving window implementation that we could use that would just calculate our result. But for quantiles, there is no like sliding window implementation that can do this in a single pass. So if someone's here who is like capable in C or Rust and is bored this weekend, feel free. This sounds like an interesting topic. And so what we have to do is we have to use a helper function for Xarray that is for more general purpose workloads. And that is called construct, which basically injects a new dimension into your array. So our simple example is we have values from 0 to 10. And the construct then converts our one-dimensional array into a two-dimensional array. And this line is basically the center of our window. And it just adds the neighboring windows as a row into the array for each center window. This is also where the complexity comes in with using this function. As you can see, like we increased our array by a factor of 5. If you do this in NumPy, then NumPy is pretty clever about this, and they only do this with views. So your in-memory size actually doesn't grow, it's just how they represent the data. But views don't really work in distributed computing, so we have to like materialize this result. So if you start with like a terabyte and increase it by 5, you're at 5 terabyte. If you do this again, because you need another dimension, you end up with 25. And that's how your dataset can grow very large, even if you started as like small thing. We actually needed a second dimension. So what we wanted to do is like smooth out the outliers, but we weren't only using like the time values linearly, we were also using the neighboring years. If you use like all of January, then you would use all of January for 2020, 21, 22, 23, and so on. So our rolling window basically got into 2 directions, like one to the right and then one down. So this translates into like 2 computations. Again, this is our input array, 35 gigs. And then we were using like a rolling window dimension of like 30, not 5. So each time we apply this, we basically increase the size of our array by a factor of 30. This is not something I made up. This is a real world use case. So the first one will bring us to 1 terabyte. Then we do a sort that's technical and make it easier to follow, so that instead of like sorting monotonically, we will sort by the day. And then we do another rolling construct. That's again a factor of 30. So we go from 1 terabyte to 30 terabytes. This is like part of the complexity when working with array data, is that as soon as you inject a new dimension into your array, you're basically multiplying the dataset size. Like if you use a large, like distributed tabular data system, you might have like tens or hundreds or maybe thousands of columns, but most of the time it will always scale by the number of rows. Like an array, especially in the geospatial world, can scale into any dimension. So you might have like, as we did, like 400 and 500 coordinate points, but then we have like 50,000 years. And that was only daily frequency. If you would run this with like hourly frequency, you would add another 24x. And then you might have another dimension that adds another 10x or so. So geospatial datasets can grow very large very quick. That's why like a medium-sized geospatial computation normally runs at least on terabytes of data, and the really large ones have hundreds of terabytes to process. And then in the end, we do our quantile. This will become important later and show us why like the free-threaded Python world will help tools like Dask a lot. So we now go through each individual step and look at where Dask screw up and could do things a little better. The first one seems pretty simple. Like we just do a rolling and then a construct. So we inject a new dimension. Unfortunately, what Dask didn't pay attention to is that you should adjust your chunk sizes if you inject new dimensions on each chunk. So what ended up happening is like we had 200 something megabytes chunk in the beginnings, and then we injected a new dimension with like size 30. So our chunks increased also by the size of 30. And if you run on a typical like Dask infrastructure, then I wish you a lot of fun running like with 9 gigabyte chunks. That won't be fun at all. So this was the first thing where chunk sizes really like broke the workload. So that's why also the person who brought us this benchmark wasn't able to run this at all, because here at the latest things would fall apart and your cluster would just run out of memory. Yeah, this is the factor of 30x. Then the next step, I cheated a little bit and added a manual read chunk in the beginning so that the 30x wouldn't be too bad. So we ended up with like 200 megabyte chunks again. And then we added the sort. Sorting in array world is similar to the tabular world. It mostly requires a complete reshuffling of all your data. So you reorient all your rows. The problem in the array world is that you don't only have like one thing that you want to reshuffle, you have like lots of chunks next to each other in the x and y coordinates normally. So you have to basically multiply the work you do for tabular data with like a few hundred at least. So what Dask does here is like it picks the 1st of January from each each slice of your data and then places them next to each other in the end. Same for the 2nd of January and so on and so forth. Obviously, like the implementation that Dask did tried to be clever because normally you have to communicate with different chunks, but Dask said, oh yeah, screw that. We will just like create tiny output chunks so that neighboring chunks don't have to talk to each other. That is not a good idea because if you do that, then you end up with like our time axis got like sliced down to 1 instead of like, I think we had 100 something before. And we ended up with lots of chunks, like 765,000. Just to represent like 1 terabyte of data. If you end up with 700,000 chunks, that might be fine. But if you do lots of follow-up computations, each computation will add like close to 1 million tasks to your computational graph. So if I add +2, it will add another 1 million tasks. If I like then divide by 2, we will get another million, and so on and so forth. So this makes things like very hard to work with if you have downstream code that runs on whatever you're sorting by. So like this is like basically, this will technically run because you end up with small instead of large chunks, but it will just overload your cluster and kill your computation in this way. So indexing basically created 1 task per time axis element times the number of chunks you have along the x and y axis. So that's not great. Obviously, like I highlighted, tiny chunks are bad. Generally in Dask, computations should run like at least a few hundred milliseconds. If you compute a sum or whatever or an S type on a NumPy array with 2 megabytes, this will be like almost instant. There is no real delay or anything, so the scheduler and the general Dask system will be very, very busy. This will like then kill you from another angle. The chunk size fragmentation is something like that took us months to work out of the Dask API. This was like everywhere. Dask tried to be clever to avoid cross-worker communication, but then it like fell over in other areas. And then downstream computing was very hard. And then we have the map. This is actually funny because this was very unexpected. Like we have the construct here again that will increase our chunk sizes by like 30x. Same as we've seen before. The interesting thing here is if you call this in a group by context, like the factor isn't 30, the factor is like 900. Because it squashes the time axis together and injects a new dimension. So you basically go from like 2 megabyte chunks to like 2 gigabyte chunks. If you started with like 100 megabyte chunks, we would now speak about 10 gigabyte chunks. I actually saw a real world workload that a user brought to me that ended up with like 8 terabyte chunks for a like 2 petabyte array. That won't run on any machine here. So this was basically another like issue that again ran into the chunk size problem in a different place and caused a slightly different outcome. But as promised initially, like we now have like 31 terabytes of data instead of like our 35 gigabyte case. And if you do something weird with Xarray, then this is actually something that happens pretty often, that you start with a like medium-sized data set, but then for some reason in downstream, you end up with like 10, 100x of what you initially started with. Yep. So and now this is my personal favorite. Like we started from the beginning so that we could run this workload and fixed one bug after another. Some of them were a little more bug than others. And then we ended on the quantile, and like it's just a quantile. Like this can't be hard, right? Turns out that's not quite correct. I have a video here of a screen recording that I wanted to show. So this is a quantile calculation on my local laptop on like I think 4 gigabytes of data, so very, very tiny. These green tasks are the quantile tasks. As you can see, this is not my video. This is really not really processing. Quantile was super slow in a Dask context, and this required lots of digging. The underlying issue is that NumPy only implements like one-dimensional quantiles. So if you have a 3-dimensional array, they just call their one-dimensional implementation over and over again, and then they jump between Python and C. So you constantly acquire and release the GIL back and forth. In a single-threaded environment, like if you run this on your local machine, then things aren't bad because like you don't have to worry about the GIL. But if you run this Dask with multi-threading, then this going back and forth between the C and Python is really, really bad because your tasks will spend more time waiting to acquire the GIL than actually like processing anything. So I've seen like workloads where one individual quantile that ran in NumPy in like 5 seconds took like 100 seconds in Dask, because the Gill convoy effect just influenced each other so badly that it basically became unrunnable. So like this will finish, like this takes 3 minutes, and the tasks will like just take forever. So what we did here is interesting. Like a quantile isn't that hard to calculate if you don't care that much about performance. You just sort your array and then pick the value you care about. It becomes a little more complicated if you have nans and like quantiles that don't exactly match one specific index, but that's all things you can handle. So we rewrote the NumPy quantile implementation with just NumPy function calls, basically sorting and then indexing. The advantage is that this is like is multi-dimensional instead of one-dimensional, so the guild problem went away. And even if we were like 5x slower than NumPy on a single-threaded environment with Dask, this just scaled linearly because the guild contention wasn't there anymore. And so like this is basically instant. There's no delay anymore. These are all the issues that we found into this like single, relatively small example. There were many, many more. That just as a teaser. So now, if I just run the code that I showed you, Dask will handle all of this automatically. Like it will adjust the chunk sizes dynamically. It will make sure that they are not too small, not too large. It will try to keep the number of chunks in check. And you basically end up with chunk sizes that were initially the same as in your output. And your array just scales up as much as you need. So, and this is another quick demo before we are done. I have to reload this. This is like a real example of running this like on a cluster with like, I think 150 machines. And Dask takes a while to actually get started and show this dynamically here because we have like over 1 million tasks. This is quite a lot. But as soon as it processes the initial overhead, things are running fine. Like memory is still a little bit of a problem, but Dask will handle that automatically for you. And then you basically end up with a computation that runs reasonably well. The red in this case is expected because we have to transfer lots of data to increase our chunks by that much. Generally, that's a bad sign, but for us, this is okay. And then this will finish, I think this ran like 20 minutes, but like 20 minutes on 150 machines isn't that bad to process 30 terabytes of data. And more importantly, it ran very stable. There weren't any issues along the way. I won't wait, otherwise I'll run out of time. A few sentences about the things like we learned and that we already kind of knew from the data frame world. Like Dask really sucked at large-scale array computing when we started. Like most of the benchmarks just didn't run without hacking around and working around issues that Dask had. But like one thing that was like confirmed is what you saw earlier. We had like 5 different issues that all crashed our workload in a different manner. Distributed computing in general requires you to do all things like reasonably well, but if you are like really, really good at something, that won't really help you in the long run. It's more like if you don't suck at anything, then you will be acceptable performance and scalability wise. And now Dask is kind of okay. Like most of the things that we see are now running. They are not as fast as we would like them to be, obviously, but they at least can be processed and are not killing the cluster in one way or another. So that's it. Thank you. If you have any questions, like I'm around.